Hello, let's do a quick guide of the equation booklet that will be in the exam with you. The equation booklet contains a lot of useful information. So I'll be going through it, highlighting any laws using red pen, any definitions using green pen, any origins where needed, where the equations come from, literacy in pencil. I'll be highlighting energy using a pink highlighter. I'll be highlighting forces using a green highlighter, and some accelerations using a yellow highlighter. The next section is on radioactivity, and for me, students use these equations down at the bottom quite well, but they often get stumped on questions that involve the use of this equation at the top. So I'd like to spend some time looking at this equation. First, I'd like to define all the terms. So the lambda is called the decay constant, and that number represents the chance of an individual nucleus decaying per second usually, but it could also be expressed in per minute, per year, or just per unit time. So for example, if I was talking about a coin, heads or tails, we would say per throw, the chance of it landing heads is a half. There's half the chance. 0.5 would be the decay constant for throwing a coin. The other part of this equation is capital N that we're interested in. Capital N is the number of unstable nuclei. Okay, so this would be how many coins are you throwing? I could be throwing 10 coins or 20 coins or 1 coin. And then capital A on this equation is the number of decays per second, or per minute, or per year, depending on how the decay constant is expressed. So if we keep the analogy for coins at the moment, the chance of us throwing a head with one throw is a half, 0.5. And if we were to throw 2 coins, 2 times a half, we should get 1 head. If we were to throw 10 coins, 10 times a half, we should end up with 5 heads and 5 tails. The chance of throwing a 6 on a dice is 1 in 6, and if I were to throw 6 dice, 6 times a sixth would be 1. Throwing 6 dice, I should end up with one of them landing on a 6. So this is the decay constant, the chance of an unstable nuclei decaying per second, an individual nuclei. This is how many nuclei do you have, and then this is how many decays are you expecting per second as a result of that. These next equations are pretty straightforward. This one links the chance of a nucleus decaying, the decay constant, to the half-life of a material. So the half-life is quite a common expression. This equation's job is literally to convert between the decay constant and half-life. And then we've got these two equations that govern the decay of either the activity of the radioactive substance or the decay of the number of unstable nuclei of the radioactive substance. Most students use these equations pretty well. These are designed for use via exponential decay using the decay constant, but we could also write an equivalent expression for each of them, that instead of using an exponential, we could say that we would like to times this by a half for as many times as the half-life has gone by, 0.5 t over t half. So say, for example, if the half-life was 2 years and 4 years has gone by, 4 divided by 2 would be 2. That would be 2 half-lives have gone by. We would be timesing the activity by a half twice, half and half again for 2 half-lives.